In this lecture, we'll continue our discussion of the quantum Fourier transform algorithm, and we'll construct a quantum circuit that would perform the quantum Fourier transform on a set of n qubits. So last time we derived an important identity. So let's review that, which will be the basis of the quantum algorithm we will be using to perform a quantum Fourier transform. So we said, let's say we have a system of n qubits. So n qubits, then we have 2 to the n basis states that we can represent as J1, J2, up to Jn, where each of these can be 0 or 1. So that gives us 2 to the n combinations. And then we represent that by just state J. So this bit string, this sequence of zeros and ones, can be thought of as the binary representation of the number J. So number J goes from 0 to 2 to the n minus 1. So again, J would be so it's J1 times 2 to the n minus 1 plus J2 times 2 to the n minus 2 plus up all the way up to Jn 2 to the 0. So 0 to n minus 1, we have J terms. We also introduced a notation 0 point, let's say J1, J2 up to Jn or Jm in general. It doesn't have to be the number of qubits. It can be just 1, 2, or as many. And that's shorthand for J1 over 2 plus J2 over 2 squared plus J3 over 2 cubed, all the way to Jm over 2 to the n. So using this, the identity we showed was that if the Fourier transform performs this operation, it takes the state J, let's say, and sends it to 1 over 2 to the n over 2. So that's the square root of the number of states. It's the square root of 2 to the n. Sum over J equals 0 to 2 to the n minus 1 of e to the 2 pi I jk basis vector k. So that's a unitary transformation on these vectors. This, last time we showed that it can be written essentially as a tensor product. So we're saying, let's say J that has this representation, J1, J2, Jn, is transformed under the Fourier transform to this particular tensor product of states. So it's going to be 0 plus e to the 2 pi I 0 point Jn, state 1, tensor 0 plus e to the 2 pi I 0 Jn minus 1 Jn, state 1, tensor with, we keep going, and every time we add one more bit here. So ultimately for the last one, we're going to get 0 plus e to the 2 pi I point J1, J2 up to Jn, state 1. So this would be for qubit 1, this would be for qubit 2, this would be for qubit n. So where we get n digits here. And of course, this has to be normalized. So we divide it by 2 to the n over 2. So now, so this tensor product structure is quite useful because essentially we know what the state of each qubit is that we want to prepare upon the Fourier transformation. So we can start playing with this. So let's say I just have one qubit. Okay, so if I have one qubit, then I have a state J1, which should be sent to 1 over, let's say, 2 to the 1/2, then 0 plus, well, the first one and the last one are the same. So e to the 2 pi I point J1, state 1. Okay, so what is that? So that's a Fourier transformation on a two-dimensional space. So you have state 0 and 1. Well, if J1 is 0, we have e to the 2 pi I point J1 is, point J1 is again 0, right? It's 0 over 2, which is 0. So that's equal to 1. And if J1 is 1, then e to the 2 pi I point J1 is e to the 2 pi I J1, which is equal to 1 over 2. 1 over 2 e to the pi I, 1/2 cancels the 2, so that's minus 1. So we see that here the Fourier transformation is just a Hadamard gate, because we know h times 0 is going to be 1 over square root 2, 0 plus 1. And h times 1 is 1 over square root 2, 0 minus 1. And that works, right? So if J1 is 0, we get the sum. And if J1 is 1, we get the difference. Both cases are normalized. Okay, so we know how to make like one of these things. Point 0.1 digits. Now, if I have more, then what can I do? So we're going to introduce a certain one qubit gate that will be useful. One qubit gate. So I call it RK, and it has a diagonal unitary operator. 1 e to the 2 pi I over 2 to the power k. So for k equal 1, this is like 1 and minus 1 on the diagonal. Now, consider a system of 2 qubits now. And let's say I take one of them. So let's say J1 comes in, J2 comes in. I take J1, hit it with a Hadamard. So I'm going to create over here, what I create when I hit it with a Hadamard is going to be that combination. So that's what's leaving the Hadamard. And now consider I take this. So I'm not messing with J2. But what I can do a control R2 here. So this control R2, when J2 is equal to 1, multiplies, it doesn't do anything to 0, right? So let's write the action of RK actually. So RK acting on 0, it has a 1 there, so it always gives me 0. And RK acting on 1 gives me that number, e to the 2 pi I over 2 to the k times 1. So now this control R2 when J2 is equal to 1 gives me, doesn't change the 0. And hits this with e to the 2 pi I, let's say, so R2 times 1 then is e to the 2 pi I over 2, state 1. So when J2 is equal to 1, right, I take this 1 and multiply it by e to the 2 pi I times, times 2 to the 2, times a quarter. And when J2 is equal to 0, I don't do anything. I don't make any change. So one way to represent this relationship is if RK acts on some state J, essentially it gives e to the 2 pi I j over 2 to the k, right? Because for j equals 0, that's the identity. So we'll see what this is doing. Here, the state I'm getting is 1 over square root 2. The 0 doesn't change whether R2 acts or not. The 0 stays the same. And then when J2 is equal to 1, this acts on this other guy, and it gives me e to the 2 pi I. I have, can write it as J1 over 2, that's this point J1, plus J2 over 4, right? Because when J2 is equal to 1, it's giving me 2 pi I times a quarter. And when J2 is equal to 0, it doesn't act, so it doesn't give me anything. That multiplies the 1. And J2 here remains equal to J2. So now we see that for this 2-qubit system, if I construct this circuit here, again, let's continue this. So I have J1, I have J2. So I hit that with a Hadamard. J2, I haven't done anything to it, and then I let it control the first qubit, R2, and here the state I'm getting is 1 over square root 2, 0, plus e to the 2 pi I point J1, J2, right? It's J1 over 2 plus J2 over 4, state 1. This is now, again, J2, nothing has acted on it. I can put a Hadamard, if I wish, over here and get 1 over square root 2, 0, plus e to the 2 pi I point J2, 1. So we see by this strategy here, for a 2-qubit system, I managed to produce the 2 states that appear in the tensor product. So in this expression, if n is equal to 2, I want one term with a point J2 here and another term with a point J1, J2. So I got those, except the order is messed up. So the Fourier transform would make this, the first qubit would make it equal to this, e to the 2 pi I point J2, and make the second qubit equal to that. But that I can fix quite easily. So if I produce those states and the order is messed up, there's one thing that we can do, and it's called a swap gate, that essentially takes 2 qubits and swaps their states. So of course, this doesn't violate the no cloning theorem. No copies are made. It's just 2 states are swapped. Okay, so I can do that, and then this performs a Fourier transformation on a 4-dimensional space for n equal to 2. So how does a swap gate work? Well, the notation for a swap gate is this. What it needs to do, it needs to take 0, 0 to 0, 0, take 0, 1 to 1, 0, swaps them, takes 1, 0 to 0, 1, and takes 1, 1 to 1, 1. So one easy implementation of the swap gate is using a bunch of C-naughts, 3 C-naughts to be exact. So I want to claim that this swap gate is the same as, I put a C-naught here. So first one controls the second one, then the second one controls the first one. And finally, again, the first one controls the second one. Okay, so if you send, let's look at the states at various stages here. So here, if I have 0, 0, nothing happens, so that remains 0, 0. Again, nothing happens. None of these act because the one that's controlling is always 0. If I send 0, 1, so here nothing happens. So here I have 0, 1. Now this guy over here, the second one is 1. So now this flips the first one. So I get 1, 1. And now this is 1. So now the second guy gets flipped. So I get 1, 0. So that's swapped them. If I send in 1, 0, at this stage, I'm getting, so now the second one is flipping. So I get 1, 1. Now over here, the second one is 1. So it flips the first one. So I get 0, 1. And then this doesn't do anything. So I remain 0, 1. That's good. If I send 1, 1, so 1, 1 goes here, goes to 1, 0. Now the second one is 0, so nothing happens. 1, 0 remains 1, 0. And now the first one is 1, so that flips the second one, gives me back my 1, 1. So that's a swap gate. It's commonly used. It has this decomposition in terms of 3 C-naughts. So now if I want to do the full Fourier transform for 2 qubits, so full Fourier transform for 2 qubits, well, what I would do is, again, I do the same thing. I send in, I hit the first one with a Hadamard, then I do a controlled R2 on the first one. So that already takes care of the first one. I hit a Hadamard here. So that's what we already discussed. And then at the very end, I swap these 2. So that would be my full circuit for a Fourier transform on a 4-dimensional space. Okay, so this approach that we talked about, we can continue this, right? So suppose, I have J1, J2, J3. Now, what I can do if here I want to get 0 plus e to the 2 pi I point J1, J2, J3, I can do, I can put another controlled here, controlled by J3, and hit it on J1. But now instead of an R2, I can do an R3. So that would give me a factor of e to the 2 pi I divided by 2 to the 3. So that creates this next digit, essentially. So let's keep going with this recipe here. So if I have 3 qubits now, let's just worry about the first one. So I hit it with a Hadamard. I let the next one do an R2 on this first qubit. And I let the third one to do an R3. And the effect of that will be 1 over square root 2, 0 plus e to the 2 pi I point J1, J2, J3. So now let me try to do the point J2, J3 on the second one. So here I'm sending J1, here I'm sending in J2, here I'm sending in J3. So at this stage, I made this, these two guys haven't changed. They're still J2 and J3. Okay, so now if I want to change my J2 to 1 over square root to 0 plus e to the 2 pi I point J2, J3, I can play the same game. I hit it with a Hadamard again. And then allow the J3 guy. So this Hadamard just gives me like a factor of point J2 now. Depends on the state of that qubit. And now I do another R2 here. So that gives me 1 over square root 2. Don't seem to have enough room here. So here, let's write it above it. 0 plus e to the 2 pi I point J2, J3, state 1. And finally, I have this last one. I just hit it with a Hadamard. And that gives me 1 over square root 2, 0 plus e to the 2 pi I point J3, state 1. So this again produce the correct states, these 3 states that appear in the tensor product. Now the only thing I need to do, so if I continue this circuit, this has like this state should be the state of the last one. And this state should be the state of the first one, so I can do a swap between the first and last to fix the order. So that's the general algorithm. We can keep going, try to draw the more general picture of this Fourier transform algorithm. So let's say, yeah, let's try to draw this schematically. So suppose I have J1 coming in here, I have J2, and then we go all the way to, let's say, then I have Jn minus 1 and Jn. So these states are coming in. So here I hit a Hadamard, I do an R2 here, control rotation, Then I would do an R3 with the third one. This keeps going and this pattern continues. And finally, I do with J n minus 1 on the first one. I do an R n minus 1 with Jn. I do an Rn. And then this is done. So what I get here is going to be 0 plus e to the 2 pi I point J1, J2 up to Jn, state 1. And so far, none of these have changed, right? So 2 up to n, they've never been controlled. They've only controlled the fate of the first qubit. So now I can play an identical game on, let's say, so keep going here. So 1, 2, etc. n minus 1n. So now I can leave the 1 out of it. It's already done. Then I play the same game on the second qubit. So I hit it first with a Hadamard. Then the next one is going to control it with an R2. So then this n minus 1, this 1 to last qubit is going to control it with an Rn minus 2, right? Because it starts from R2. So now the third qubit applies an R2. Here, the second qubit was applying an R2. And the last one finally gives another. So here there are a whole bunch of them for these intermediate ones, R2, R3 up to Rn minus 2. And then this one applies an Rn minus 1. So if I do that, then the second qubit becomes 1 over square root 2. I have 0. I have e to the 2 pi I. So now this structure starts at J2 and goes all the way to Jn. And then we can just keep pushing. Now for the third one, I again hit a Hadamard, hit everything below it. I start with a controlled R2, then a controlled R3, and I go all the way to a controlled Rn minus 2 in that case. So let's keep going with this structure. So let's think about the qubit J minus 1, the 1 to last. So that's one. Again, when I'm happy with qubit J minus 2, when that's done using the same structure, again, I start with a Hadamard. I hit an R2 here, and that's that. So that gives me this 1 over square root 2, 0, plus e to the 2 pi I J n minus 1 Jn 1. And then this one, if I want to fix, I hit a Hadamard for the last one, and I get my state. So now I essentially got the Fourier transform, except the order is reversed, right? So what should be the state of, sorry, this is n minus 1, and that's n. It's qubit n minus 1 here. This is qubit n. So what should be the state of the last one is the state of the first one. So I can put a bunch of swaps to fix that. So for 3 qubits, I fixed, I just swapped the first and last, and that fixed the order. So let's say I have 4 qubits. So I have 1, 2, 3, 4. And what I get the correct structure, except it has like a 4, 3, 2, 1. So what I can do is, well, swap these two and swap those two. So if you do something like this, and then something like that, this goes back to 1, 2, 3, 4. Similarly, if I have, let's say, 5 of them, So I end up with 5, 4, 3, 2, 1. So I can swap the last two. So that brings a 1. That's say to the end, this say to the beginning. Then I swap 2 and 4. So that takes care of that. And 3, that's in the middle, just stays where it should be. So that's kind of the structure. A linear number of swaps in the number of qubits would fix the order. So we have a complete algorithm that performs a Fourier transform on an n-dimensional space. And then, of course, if I send in a superposition, so send a superposition, let's say sum over j xj j, where these are just some complex numbers. They have to be normalized, but it doesn't matter. Like you can always normalize and send them in. Then as I apply my unitary on this and I perform that change of basis, as we showed last time, this really produces a superposition sum over j yj j or yk. It's just a dummy summation variable in this case, so it doesn't matter, but let's write it as it's k. So then essentially the amplitudes get transformed in the standard computational way. Now let's think a little bit about this circuit. So essentially, if I wanted to perform a Fourier transform on a bunch of numbers, so let's say, so if I wanted to get yk to be equal to 1 over square root of n when capital N is 2 to the little n, the number of qubits, so it seems that to get each of the y's, I have to perform n operations to find the terms of in the sum, and then there's n of them, so it's like n squared. So naive classical algorithm would have 2 to the 2n operations. It's exponentially large in the number of bits in little n. So that seems slow. This is actually not the best classical algorithm. There is a faster algorithm known as the fast Fourier transform, which essentially uses kind of a similar structure to what we showed to that tensor product. And that goes like n times 2 to the n. So still exponential. Now let's think about our circuits. So how many gates do we have here? Well, if I think about the number of gates, well, it seems the first one has like n of them, right? Rough, yeah, so there's a Hadamard, then R2 up to Rn. The second one is going to have n minus 1 gates. It has one less gate. The next one has n minus 2. So number of gates in quantum Fourier transform seems to be something like n plus n minus 1 going all the way to the 1. The last one only has one Hadamard, it seems. So that adds up to be like n times n plus 1 over 2. Then there's another n swap gates. So seems it's quadratic plus some linear correction. So there's like an exponential difference between the number of gates in the quantum algorithm and the number of operations in the classical algorithm. So that, on the face of it, looks really great. But there are some complications, of course. It's not necessarily always useful. So the idea is, like, if you think more carefully, so there's going to be that superposition that's there, but those numbers that appear in this final superposition that the circuit produces, the output of the circuit, it's going to be hard to access those numbers directly by measurement. So we can't, like, reading off the whole state for a large number of qubits that's going to require many measurements. It's going to be complicated, because every time you measure, you're going to get, some random number, and you have to repeat the measurement many times. That just tells you something about the probabilities. So if you have an exponentially large number of possibilities, you have to perform the measurement many, many times. Furthermore, how are we going to prepare this initial superposition? So if I hand you a list of classical numbers, xj, well, this input that gets transformed to that output, how are we going to make that input superposition? So just to use it to do Fourier transform, it seems it's not obvious what to do. So we need to look for very special problems where this approach can be utilized. So yes, so mathematically there is an exponential difference in the number of operations in the best classical algorithm and this quantum algorithm, but we need to find problems that can take advantage of this without complications having to do with measurements or preparing an initial state that I would pass to my quantum algorithm. So Fourier transform is the basis of an algorithm that we'll talk about next time, known as quantum phase estimation. And of course, the crowning achievement of these types of ideas is the Shor's factoring algorithm. So if you have an integer, a very large integer, classically, it's very hard to find its prime factors. It's very easy if I hand you a set of prime numbers and multiply them and get an integer that has those numbers as prime factors. But factorizing an arbitrarily or a very large integer into its prime factors is a computationally expensive, exponentially hard problem. And these ideas that build on the quantum Fourier transform through Shor's algorithm can actually perform that task in a way that's exponentially better than anything the classical algorithm has been able to achieve. All right. I think this is probably a good place to stop. So next time we'll continue with the phase estimation algorithm, which is an algorithm that's really the basis for many different quantum algorithms, and it has many applications. All right.